Welcome back to school. I hope that you had a good spring break. I will let you know that we are all really distressed that we're not going to get to see you guys again this year, but we're going to continue doing things this way. It's not ideal, but we'll just do the best we can. Today we're going to start talking about what's called electromagnetic radiation. You know that in order to see something, there has to be light bouncing off of it. I have some students here that are studying and helping learn. So thank y'all for coming. Talk about what light is. First of all, light is sort of the everyday word for electromagnetic radiation. Okay, and this is abbreviated as EMR. You know from previous units that when an electric field moves, like there's a current or there's a charge moving, remember with our right-hand rule, if there is a charge moving through a wire, it creates a magnetic field around the wire. So when current is moving, a magnetic field is created. And likewise, when we used a generator, we shook a magnet inside a coil of wire, we made the magnetic field move, and that created an electric field. Those two fields can oscillate back and forth. That's what makes up electromagnetic radiation. So electromagnetic radiation is made up of oscillating magnetic and electric fields. Okay, we can model this oscillation as a transverse wave. So a lot of times you'll see light modeled as a transverse wave. Light is interesting because light is a transverse wave. And during this unit, you're going to see that there's evidence that it acts as a wave. But there's also evidence that light acts as a particle. It's called a photon. Okay, now as you know, light moves very fast. In fact, it takes only 8 minutes from the light to move from the sun to the earth. The speed of light is 3 times 10 to the 8 meters per second. And this is what we'll use for our class, for our calculations in class. The letter C, that's just a velocity. You can use that in this equation that we all know, velocity of a wave. You need to use this equation as it pertains to light. But now, a lot of times our velocity is going to be 3 times 10 to the 8 meters per second. That's really fast. Light is different though than mechanical waves. We know that mechanical waves like sound, the wave on a slinky, an ocean wave, what do they have to have in order to transfer energy? What do they have to travel through?
A mechanical wave needs a medium.
That's right, they have to travel through a medium. Okay, now light is not like that. Light does not need a medium to travel through. In fact, light can travel through the vacuum of space. Light does not need a medium to go through. Hard to imagine how much distance is between objects in space. I'm sure you've studied the solar system before, so you're aware of these huge distances. But if you think in terms of the distance to the next star or the distance across our entire galaxy, you have to think in terms of what's called a light year, the distance that light travels in 1 year. Okay? And you can imagine that would be really, really far. How far is a light year? Okay, so we start out with 3 times 10 to the 8 meters per second. We want to know how far light goes in 1 year. Hours in a day, 365 days in a year. So I'm getting 9.5 times 10 to the 15 meters per year. Kilometers. Now, that's a really big number. So outside our solar system, which is our sun, of course is the closest star, but outside of that, the closest star is called Alpha Centauri, and it's 4.4 light years away. So it takes 4 years for light to get from that closest star to us. So it's pretty impressive distances, I think. So next I want to talk to you about the whole electromagnetic radiation spectrum. What we call light is really the visible portion of that. and it's a very small sliver right in the middle. We can say this is the very high end, and then it gets to be a very, very, very long wavelength on this side. Here we have a very low wavelength and a high frequency, and here we have a very high wavelength, long wavelength, and a very low frequency. So if I set this up, okay, the largest wavelengths on the EMR spectrum are called our radio waves. A little bit higher frequency, those are our microwaves. Next we have infrared, and then our visible light spectrum is a little sliver right here in the middle. It's our visible light. And of course, you know visible light goes from red all the way down to violet. Frequency, then visible light is ultraviolet. And then we have X-rays and gamma. Okay, so there's a few trends that you want to know about this EMR spectrum. Radio waves have a high wavelength and a low frequency. Okay, gamma rays down here have a very low wavelength, very short wavelength, and a high frequency. Okay, so radio waves are not harmful. They're actually everywhere. Radio and microwaves are used in a lot of communication. You know radio waves, FM, AM stations. Microwaves are used in cell phone communication. Infrared waves are heat, that's just heat waves. And then of course you have the visible spectrum, where red is your lower frequency, violet is your higher frequency. You are going to talk about this more, these colors this week. Ultraviolet rays, you know those are dangerous. That's why you wear sunscreen. UV light, okay? Have you looked on your sunblock? It says UV, protects from UV rays. That's what it's talking about. You go to the doctor's office and get an x-ray, they put the lead apron on you to protect your body because these can be harmful. Gamma rays are extremely harmful. Luckily, our Earth's atmosphere blocks these harmful rays so that we stay safe here on the surface of Earth. Get an idea of the size that we're talking about of these wavelengths. On the very left-hand side, you see radio waves about the size of buildings down to the size of human beings, down to infrared being about the size of a honeybee and then a pinpoint. So you can see all the way to the right-hand side with gamma rays, they're very, very, very small wavelengths. So I wanted you to take a look at this image so that you could get a better idea of the range of wavelengths that we're talking about here. So let's talk about energy. In the last unit, energy was related to amplitude. All right, in this unit, I want you to think about energy as higher frequency. Radio waves have a very low photon energy, not harmful. And then it gets higher, higher, higher until you have gamma rays, which have a very high photon energy. As frequency increases, photon energy increases, and if photon energy increases, the electromagnetic radiation is more dangerous. Light does go in a vacuum at 3 times 10 to the 8 meters per second really fast, okay? But it slows down when it goes through other materials. So light slows down when it goes through other transparent or translucent materials. Glass, and even air. It slows down just a little bit when it comes into our atmosphere, but it's not enough to make a lot of difference to the speed, okay? When it goes through water and glass though, however, the more dense the material, the more it slows down. For example, when light goes through this glass of water, obviously this is transparent and light can go all the way through this material. It's going at different speeds through the glass and through the water. Image through this
glass is a little distorted, okay? So
it will distort whatever image that you're seeing through here because the light is actually bending. Refraction as it slows down going through other materials other than the vacuum of space, okay? So refraction is the bending of light because light is slowing down, Okay? Also, reflection. Bounces off an object. But in general, the reason that this cup looks orange is because light is reflecting off this such that we can only see the orange frequency. Let us know if you have any questions, and I hope that this was helpful. Have a great week, and we will talk to you soon. Thank you.